Okay, so last we left off, we were talking about priority and what has priority in terms of nomenclature, right? So let's see how much of that you guys actually remember. Okay, so how will we go about naming this guy? And who has priority?
Double bond has priority, yes.
Okay. So the OH has priority. Yeah.
Well, I meant over the triple.
Oh, yeah. So the double bond has priority over the triple bond. Okay, you guys got a name for me? Okay, so. Okay. So first thing we want to do is do what? We should always do count the carbons, right? Okay, so let's go ahead and count the carbons. Where am I going to start counting from? Left or right?
Right.
You said left?
Starting on the right side.
Or would I be starting over here? Okay, so the OH has priority. So then we would start on the left. That is correct.
Oh, okay.
So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. Okay, guys, six carbons? Yeah, no? We all agree? You guys, is it a Monday or what? It isn't a Monday. I don't know what day it is then. Okay, so we have 6 carbons, right? So we know that that's going to be what? 6 carbon chain. Okay, hexa. Okay, now we have double bonds, we have triple bonds, and we have alcohols. So how will we go about doing that? You were saying earlier. Okay, so you wanna, should I put the hex? The hexanol goes at the end? Okay. Okay, so you're looking at, that's the old school way. New school way. You're doing it old school way like I did when I was in. Okay. Okay, so you guys are not doing so good so far. It's okay. No, that's right. It's right. So let's think about it. What you're saying is right. The location of the ene and the ion are correct, right? You guys are saying the location right, but the order in terms of how would I write the order of it, right? So let's actually put the number in the name. Okay, so let's start by doing that. Okay, now since it's all belonging to the same chain, right? We want to incorporate that into the name itself. So it's a hex, is it double bond, single bond, triple bond? So am I going to use A because AN and then, or am I going to use an EN or am I going to use a YN? No, for the next part, for hex, is it hexa, hexene, hexine? Ooh, somebody has a. Okay, Sampula says, hexene, and she says 5 dash hexene. Are you guys, do you guys agree with that so far? I'll write down what she says completely. 1 INE, 3 oh. You guys agree with that? Okay, so it should be 4. Excuse me, 1 second. Monday. It's definitely Monday. Did you see my hair sticking up there? Nobody said anything. You didn't even notice. Okay, fine. Okay, so we should put a 4 here. Anything else? Anything else? Sure.
No.
No, what do you think, Kayla?
No, I don't believe so.
You
I
don't
think
think there's anything else?
No.
Okay, so this E here shouldn't be here, right? So we should actually not have it because it's not the very end of the compound. Okay? So this would be one way of doing it. The other way of doing it, it would have been oops. Okay, I'm having one of those days. Did you guys get that answer? Let me retype it. So it's 4. Or we could have said okay. Are you with me? Okay. Yes. Yes. And that's the way you should do it. The only time that the other things go in front is if you have side chains, or substituents that are off the chain, right? And so otherwise they should be part of that name, right? And so you're telling me that this is a hexene and all of those things are incorporated in it, okay? And so that's really important, okay? As I said, old school way, right? You could have got a way of putting that on the outside because then it's understood, but now they've incorporated in the name, okay? And you'll see, the problem is that you'll see it done the old school way when you're looking at chemical compounds. They'll put it in different ways. They'll put it the new school way and the old school way. Okay?
So, which one do you want us to use? Because the book, I think, has the top. Does the top?
Yes, the book has preference for the top, but both of these they're both accepted. And the book actually makes reference to that you could actually put the numbers in both. Okay.
Oh, okay. So we can use either or.
Yeah.
Right? Okay.
But be familiar with either or.
Gotcha.
Okay? Does that make sense?
Yeah.
Okay. And so we know that we're going to base it upon priority. Okay. And then I gave you guys the priority list. Did I already give you guys that? last semester? Okay. So you want to start memorizing that. That should be something that you know. Sorry, organic chemistry is memorization. You got to memorize. Okay. Okay. Yep, that's it. Okay, so let's keep moving forward. Yes, I'll be collecting those. So remind me at the end, because otherwise I will forget. So the structure of alkanes, right? So we know that when we're talking, alkenes. We know that when we're talking about alkenes, what is the hybridization of an alkene? Alkene. Are you sure? Alkene. What was that? Are you sure? It's just SP. What was that? Now, don't think about you're getting a mistake with pi, right? So don't mistake pi for your hybridization, right? Okay, so here we have, in the case of, you have these two carbons, right? And let's say you have the sp-sp overlap here, right? So each of the carbons, because they're only going to be forming one bond, they're going to be sharing one with carbon and one with the hydrogen, right? So it's going to have an sp hybridization that's going to be associated with it. It's not like it has four. In that case, it would be sp3, right? If it had four attachments to it, or if it was going to have four attachments to it. Does that make sense? So that center atom, that carbon, is only going to have an sp hybridization. It is only going to need to use the s and the p, right? Because then you have the other two p's that are available for that triple bond forming. And we know that we have a sigma bond and we have two pi bonds in this case. Okay, does that make sense? Do you guys remember that? Sigma bonds and two pi bonds. No, it's so the pi bonds are actually the hybridized orbitals typically only form sigma bonds. Okay, the pi bonds are typically formed by the p orbit. Okay, so, and we talked about that. I mean, I know we rushed through it, and I think that's part of the problem. And then we do what we all do best, is like we memorize it for that exam, and then we all dumped it out at the end of the semester, right? So that's what we typically do. So, but the thing is that for organic chemistry, we have to start paying attention to that hybridization, because it helps us understand the structure. It also helps us understand what is going to be accessible. What are we going to be able to bond with, and how are we going to be able to break those bonds? Okay, so we know, or we should know, that when we have a triple bond, it's going to form a linear structure, right? And that's part of the reason why you see me drawing the line things, then you'll have a line coming out of it, because we always know that it's going to be linear, right? Where with the double bond, right, or a single bond, we could actually have kinks that are occurring, right? We could have a cis or trans chemical as a result of it, because it's a double bond and a single bond, right? Where if it's a triple bond, it's going to be linear. We're limited by it being linear, okay? And that's going to be kind of important for us to kind of understand some of the physical features, right? Because if it's linear and it's not kinked, how's it going to affect our boiling points? Do you guys remember how is boiling point and melting points are affected? Say that again. The amount of surface area. So if something is linear, rather than kink, how much surface area are we going to have in each one? Which is going to have more surface area associated with that molecule kinked or that molecule that's linear? And we have to think about accessibility of another molecule interacting with it, right? Because do you guys remember what kind of dictates the boiling points and melting points? Statement at home. Say that again. Intermolecular forces, right? Intermolecular forces, intermolecular forces, right? That is correct. Remember the answer to everything, intermolecular forces, right? Okay, so the more surface area that we have, the more area that you have to be able to contact, what would you expect to happen? Yeah, more surface area. The higher the boiling point. That is correct. So that is correct. So the boiling point is going to increase as the surface area increases. So if you have two molecules, you have one that's a terch, a one that's a neo, and a one that's an N, right? Which one is going to give you more surface area? The N, right? Because the N is just a long chain, right? That's connected, okay? Now the N would have the longest one, right? So we know that that surface area is going to play a part. Now that's also going to be the case in terms of double bonds and triple bonds, right? Because if it's a double bond, we could have trans, we could have cis. Okay, now if it's cis, are you going to be able to get in contact with all of the different elements there, right? Compared to where it's linear. Yeah, something that's like this, linear. Can you guys see me? Oh, linear, right? Or let me draw it on the board. Yeah, it was the top of my head that was showing. They got to see my little one braid standing up, you know. So, this is not working out right. Okay, so for okay, so we have these three structures. We have say 1, 2, 3, 4. So this guy would be cis or trans. Okay, cis what? Cis what? Cis 2. No, you not that. It's tetra. Okay, so it'd be cis 2 butene, right? This guy would be called, was it? Okay, so this would be called 2 butyne. Okay, and then this guy would be called okay. Now, which one has more surface area? Which one, we have more contact of another molecule like itself touching? The butyne, right? And so we would expect the butyne to be higher in its boiling point, right? Okay. Okay. Yeah, but it goes back to that possibility of surface area. That kink, these kinks are going to affect that possibility, right? Okay. No. Okay, so but that's intra, right? Intra forces, right? So we're not breaking those bonds in the case of boiling points. We're just allowing them to separate. Do you understand? So that's intermolecular forces. Okay. Okay, so if we sit there and we look at it, it pretty much pays attention to that order, right? So here we have ethane, propane, butane, pentane, and hexane. And as we notice, the boiling point increases as the chains get longer, right? More surface area, okay? So then we have ethene, propene, 1 butene, 1 pentene, 1 hexene, cis butene, trans butene, okay? So we have if we take a look at these guys compared to the butane, and then we'll take a look at the 1 butene compared to it, right? Okay, and then if we take a look at the propene compared to the propane to propene, right? So those, in this case, the single bond has a higher boiling point than the double bond. Okay, and then when we look at the 2 cysteine and the trans 2 cysteine, so the cis 2 butene and the trans 2 butene, then the trans 2 butene has a lower boiling point than the trans 2 cis. Okay, why is that? So why is it this guy compared to this guy having a more contact, or having to require more energy for it to be separated?
More stable.
It's not the stability. Well, you're not, again, you're not breaking it apart. It's not being, dissociated. It's still gonna be cis 2 butene. Like, what is it about the cis 2 butene interaction with cis 2 butene that'll allow it to sit there and be more connected than the trans 2 butene? Okay, so and by them being closer to each other, what are they doing? Rather than them being opposite of each other. What was that? Did you say pulling from each other? What is that called in chemistry? What was that? Polarity. Okay, because it has more polarity than the trans does, right? That polarity is causing the dispersion forces to interact. And so it's pulling a little bit from each other, the electrons, okay? A lot more than what you would get in the case of the trans. Are you guys with me? Can you see that? Can you imagine that? I know it's not pretty. That's right, yeah. And so you're not getting a nice pull where these guys having more of a pull that's associated with it. And because they're having more of a pull, they're going to be interacting more so with each other. Okay? And then that's the same thing that's going to happen in the case of the triple bond. right? Not only do you have the surface area that's contributing to it because it's all nice and linear, but you also have the polarity of it. Okay, so triple bonds are going to have a higher polarity than the single bond. I mean, the double bond, typically. Okay. I want you guys to bring your modeling kits. Okay, so start bringing those on Mondays. Okay, wait. Okay. I have to keep my chat open. You guys are not doing too bad today. You're interactive, you know, it's a good thing. Okay, so this basically is just showing you the case of the triple bond, right? And so we have 2-butyne. We compared that, if we go back and compare that to the other two values, right? One was 0.5 and one was like negative something, right? I can't remember. I'm old. Sorry, 3.7 and I'm way off, and 0.9. So if we look at the 2-butyne compared to that, which is 27. Okay. So you guys kind of understand that, and you can see the reason why, right? Okay, and that was my question for you guys. So. Okay, so let's move on. Okay, so alkynes, like alkenes, undergo the electrophilic addition reaction. So if we're reacting with hydrochloric acid or hydrogen chloride, then what will happen is we will get the breaking of the triple bond. We'll have the addition of the chlorine to one of the carbons and the addition of the hydrogen to the other carbon. And it's going to behave the same way, right? The same process, okay, as the alkenes. Okay, let's see, come on. Okay, so that means that in the case of the alkenes, it was the double bond was providing the electrons to the hydrogen. Then the hydrogen was providing its electrons to the chlorine. Okay, and then we'd end up with an aqueous cation initially, and then we'd have that chloride, and the chloride would end up acting with that positively charged cation, right? You guys remember that? Yeah. Okay, now this is going to be the same thing that's going to be happening in this case, right? With the triple bond. Triple bond now is going to be providing the electrons. Okay, so those electrons are then going to attack the hydrogen. The hydrogen is then going to let its electron be provided to the chlorine, right? So then the chlorine becomes negatively charged. The hydrogen is going to attach to the carbon, one of the carbons. One of the other carbons is going to have a plus charge associated with it, so it's going to form a cation. And then the chlorine is going to then attach to that. Okay. Make sense? Okay. So it's going to be that same process. It depends, right? Which is more, it depends on where the triple bond is located at and which is more accessible and which preference, right? Because there is going to be a preference associated with it. And it's also going to be dependent on how much of the HCl you have. Okay, that also plays a part in it too. Okay. Okay. So you guys remember relative carbocatenation stability? from last chapter?
Yes.
Okay. So if we have hydrocarbon, 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 and then that carbon in the middle, the cation here, this guy is going to be our most stable compared to where we have hydrocarbon, hydrocarbon, a carbon in the middle, and a hydrogen on the side, right? That's stable. And then this guy is going to be the vinyl, the secondary violic cation is going to be less stable. These guys are going to be about proportional to each other, right? So you guys remember where we have two hydrogens and then that one, a little less stable. And you want to kind of pay attention to the stability of this, because this stability is going to help us decide what our products are going to end up being, right? And then that's going to be less stable than the primary linoleic cation, and which is going to be about comparable to the methyl cation. And then that, all of those are going to be more stable than the vinyl cation, which is going to be a lot less stable than the others. Okay. Okay, so the other thing is that we're going to have to be aware of is that sometimes we're going to have the formation of the pi complex. Okay, so now we know that primary linoleic cation is very unstable, right? And because it's unstable, it's looking for a way to kind of stabilize itself. Okay, so it's going to be, we know that it's also less stable than the primary acyl cation. And so because of it, again, we're going to be forming this intermediate, what we call a pi complex, right? So in other words, we're going to have this hydrochloric or hydrochloride compound is going to be interacting with both of the carbons potentially, right? Again, using that concept of partial positive and partial negative, this guy is partial positive, this guy is partial negative, right? Now, these guys, we know that it's positively charged, right? Or the cation is going to be positively charged. So instead of forming a truly positively charged compound, what it's going to do is it's going to form this pi complex, where it's going to be interacting both by that partial charge. Okay. And today has been a busy day. Okay. So evidence for the formation of the pi complex. So this just is basically providing us, providing us with that evidence. Okay. So in other words, this guy is going to form that initial pi complex, right? And that pi complex, then it's going to act as an intermediate. So instead of how we would think about it, totally losing those electrons completely from the double bond, it's actually going to form that pi complex by interacting with the hydrogen again, but pushing those charges, right? The chlorine is going to be pulling the electron more towards itself. The hydrogen is going to be back partial positive. And so it's going to interact with that. And that's going to initiate our start. But again, that's going to be an intermediate, right? Okay. And so because we get the formation of that Z, the Z isomer, when we add the chlorine, that suggests that that happens, right? Because then you'll end up with these guys opposite of each other, anti towards each other. Right? Trans. Okay. And then that suggests that that is going to be a probable cause. What's going to end up happening as a direct result of the pi. Okay, so if we look at the energy, so this is Gibbs free energy. This is our alkane. This is our alkene. So in the case of our alkyne, in case of our alkyne, the Gibbs free energy of the pi complex is higher than that of the alkaline cation. We know that alkenes are going to be less stable than the alkyne. Alkyne is going to be less stable than the alkene, and we also know that the pi complex is going to be less stable than the acyl cation. Although we know that the pi complex is more stable than which cation? Can you guys hear me over there on the other side?
Yes.
Okay. Two messages, hold on. Okay. Any guesses?
What was the question again?
I said the pi complex is going to be more stable than which cation? No, we're not reading the graph. This is just based upon what we just talked about. Stability, who is more stable? So we know that the alkene is more stable than the alkyne. However, when we're talking about the cation, right? So is it? Look at the energy level, right? So what is going to be more stable? Think about lower energy level, more stability. Okay. Now, but I'm not just saying looking at this slide overall, because we talked about stability, right? So we know that there's one that is very unstable. What is the one that is very unstable? And that's the reason why we have to form the pi complex. Just talked about it. Is it primary alkyne? Are you sure? It's primary something. You got the primary part. Yes, vinyl. There you go. Yeah. Okay, cation. Okay, we know that that guy's going to be the least stable. Right? So you're not going to really have the formation of that. Instead, you're going to have the formation of the pi complex. Okay, so that was the whole thing about the struggling here. It's a Monday. Nothing's working. At least okay. So we know that the vinyl cation is going to be the least stable of all of them. Pi complex is actually going to fall between that. That's the reason why you have a pi complex forming. It's more stable than the vinyl cation. Okay. Come on. There you go. Okay. Let's go. Okay, there we go. Okay, questions, concerns? Cash? Okay. So we know that in this case, we're going to have the halo substitution, and we're going to end up getting an alkene, right? So the triple bond is going to be split into a double bond where it's going to have one side is going to have a halide on it, and the other side is going to have a hydrogen. Okay. Now, if we add more, then we can end up with a geminal dihalide. Okay, geminal basically means like Gemini twins. Okay, so excess HCl causes the geminal halide. Okay, so then we end up with, get rid of our double bond, we end up with a single bond. Okay, you guys got that? Okay, so we have to be careful. If we're adding excess amount of HCl, then we know that we're going to end up with our geminal dihalide rather than just the substituted alkene. Okay, so if we have 1-to-1 equivalent, we're going to end up with the alkene. If we have excess, we end up with the geminal halide. Okay, so how you guys doing so far? Brain's working? Good. What was that? Okay. Oops, sorry. Okay. So in terms of relative reactivity, alkenes are going to be more reactive than the alkyne, which is going to be more reactive than the substituted alkenes. Okay. Okay. So if I add excess hydrobromide, what's going to happen? It's going to become a twin. That's right. Yeah. If I add equivalent hydrobromide, okay. Now, this is going to be true for chlorine and bromine. When we get to iodine, that's not going to be the case. And I'll talk about that a little bit later. Okay, so question is, why are alkynes less reactive towards electrophilic reactions? A, triple bonds are stronger than double bonds. B, only a pi bond must be broken in the addition of the electrophilic, an electrophile to an alkene. C, the pi complex is formed from the alkyne is less stable than the acyl cation intermediate that is formed for an alkene. D, all alkenes are less stable than alkynes. E, hyper conjunction stabilizes the intermediate from an alkene more than the intermediate from an alkyne. What do you guys think? A, B, or C, D, or F? Oh, wait, we got answers. Sampula says A. Do you guys agree? Triple bonds are stronger than double bonds. Is it the reason why? Okay. What do you guys think? Come on. You got to think. What do we know? What do we know for a fact? Well, we do know that it is true that triple bonds are stronger than double bonds. They're harder to break, right? Okay, so that's partially true, yeah. But is that the reason why they're less reactive? Because we know that well, we know that double bonds are more reactive than triple bonds, right? Is that true? What was that? You said B as in boy? D as in donkey. Okay, D as in donkey. I have to make it harder. No, it's not D as in donkey. Was that? It's C as in cat. Yes. Because we know that complex, we have to form that complex, which is going to be less stable than the alkaline cation intermediate. That intermediate is what's going to cause our problem. Okay. Are you guys with me? You guys have that look. That means it likes electrons. So the correct answer is C as in cat. Okay. Okay. Okay, so if we have so in the case of the electrophile is going to be added here. Okay, so in this case, we're looking at the addition of a terminal alkaline regional selection. So here we have a terminal alkaline. We're adding HCl to it. So in this case, what's going to happen again is, sorry, getting carried away. We're going to end up with the chlorine going internally. So that's going to have a positive charge compared to the positive charge being at the end. You guys remember that from when we were talking about the double bonds? The alkene, where it prefers the positive charge, preferring. You guys have that book. Okay, so this guy, again, is going to shoot over here and interact with the hydrogen, right? Okay. So when that happens, we're going to have a choice. We could go with putting a plus charge here, or putting a plus charge there. Right? We know that those terminal plus charges are not very stable, right? So we're not going to do that. We're not going to want to do that, right? So it's always going to put a plus charge here, right? So that means that the chlorine is always going to end up here rather than ending up at the very terminal end. Okay? You guys remember that? Okay. So you want to make sure that you guys remember that, because that's going to be the same thing that's going to happen in the case of the alkyne, right? Exactly the same situation. That's right. Yeah. So in this case, again, this guy is going to end up having that plus charge, but instead of having that plus charge, because we know that that isn't stable, it's going to form that pi complex, right? And then when it forms that pi complex, you're going to have, again, hydrogen chlorine positive, partial negative, partial positive, and these guys are gonna do like this. At the end of the day, this hydrogen is going to be pulled away over here, okay? Allowing the chlorine to interact with this, okay? So let me show you that. Okay, so triple bond electrons are being given to the hydrogen. The hydrogen's electron is going to be given to the chlorine. So these guys are actually going to form our pi complex. Okay, so then the formation of the pi complex, these guys are also going to end up happening. And then we're going to end up getting chlorine added on to the hydrocarbon that has a chain on the other side, not terminal in. Okay, so pay attention to the R. The R means basically there's other hydrocarbons there. Okay, so we're not going to get a chlorine over here, right? Because it's not preferred. It's less stable, right? So it's going to want to put itself internal. Okay, and then that's going to end up causing the pi complex to separate. The hydrogen is going to come over at this side of it, and then we're left with our substituted halide on that secondary carbon. Secondary, okay? You guys had it look? Are you with me? At home, are you guys with me?
Mm-hmm.
Okay. Follow the arrows, okay? So this guy is a more stable transition. This guy is a less stable transition, okay? So having the chloride here is more stable compared to having it on the terminal carbon. Okay. So we got to pay attention to, is it terminal or is it not terminal, right? Because if it's terminal, we're not going to put a chlorine there, right? We're going to put the chlorine on the inner carbon. Okay. So if we have excess hydrochloric acid, again, we're going to get our Gemini, right? Our geminal dihalide. Okay. And again, it's going to go on that secondary, not the terminal, not the primary. Okay. Okay. And this just kind of shows us. Okay. So again, we have to pay attention to what is going to be more stable. Okay. The secondary carbocation is going to be more stable than that primary carbocation.
Dr. Henry, why will secondary carbocation be more stable than primary?
Just having that charge at the end, it doesn't seem to, because particularly for that carbon, that having that buffer of that internal carbon is a lot more stable than not having it, than that having it at the terminal end. Okay, so how can I say? Like this plus charge here doesn't last long, right? It isn't preferred. It doesn't have a preference. And it has a tendency of popping up. As soon as it pops up, what happens is that the electrons are going to be shuffled over here to kind of balance it out because it doesn't want to be messed with. Okay, so then the electrons that are here on this point are just going to be immediately shuffled over to compensate for it. So it's not stable. It doesn't exist long enough for anything to happen. Does that make sense?
Yeah, that makes sense. Okay, okay.
Okay, but if it's more internal, it can be buffered more, right? Because you have all of the other sides to sit there and kind of buffer it out. So it's going to be a lot more stable.
Okay, okay. Thank you.
Okay, so we talked about the excess. Sorry. Okay, so here we have a triple bond on the third carbon. So then we have the possibility of having our geminal, in this case, the geminal bromide, or geminal halide, either on the second or on the third carbon. So second or third carbon. Okay. Long as it's not the terminal. It doesn't like to put it on a terminal. Okay. So in that case, because you have both on both sides, it goes both ways, right? It'll actually put it on both sides. So us having excess amount, you're going to end up with both isomers of this guy. Okay. So in this situation, you're going to end up with the same either way, right? Because it's right in the middle, symmetric. You're only going to end up one compound. Okay. Because where it's located at. Right? So this is unsymmetric, right? And so you have the possibility of putting it on the third carbon or on the second carbon. Okay, where this guy is the third carbon, right? Regardless of how you look at it. Yeah. So this guy here, yeah, 1, 2, 3, 1, 2, 3. Right? So your product is going to be exactly the same. Okay. Okay. So here we have a unsymmetric hydrocarbon, and we're adding chlorine and dichloro methane. And so in this case, you're going to get trans chlorides. And then if we add more, we add excess of that, then we're going to end up with the addition of 4. So tetra halide. Okay, and that's the same thing in the case of the bromide. So in the case that we're adding bromine gas and this dichloromethane, then you're going to end up with them being trans to each other. And then if we add excess of that, then we're going to end up with tetrahalide. Okay. Questions? Concerns? Cash? Okay. So, and this is kind of good to see because then you know that you don't need that. The second moiety is just acting as a catalyst. It's not. It's not being utilized for the reaction. Okay. So the dichloromethane is just acting as a catalyst. Okay. or methyl chloride. Okay, so which product is expected from the reaction shown here? A, B, C, D, or E? Think about it. Would this be terminal? Are we going to get a terminal? Think about what we just talked about. B or D? B as in bear? Okay, B. What do you guys, what do the rest of you guys think? I'm gonna have to do a little other thing here. So we have C, we have B. What do you guys, tell me your votes.
B.
Abby says B. So we got 2 for B. We got 2 for B, 1 for C. Are you sleeping? You say B as in boy?
I'll go with B.
You'll go with B?
Yeah.
Okay.
Timpula said B as in boy. In the
Okay.
chat.
So we got 5 for B. Okay, got, what is that? That's 6 of 9. Need some more votes. Or did I miscount? So who hasn't voted online? Oh, I included myself. Sorry. I need 2 more votes. You said B? You would B as well. The correct answer is B as in boy. We have excess. We know that this guy, if it's here, this is terminal, right? We know that that's not going to happen, right? Because it has preference for that internal carbon. Okay. So what if it wasn't excess? What would be the correct answer? That's right. A would be the correct answer. Okay. Okay, so the correct answer is this one. Okay.
B was the correct answer.
B was the correct answer. Yep.
Okay,
B
sweet.
as in boy. Yeah, these are all terminal. Like terminal 1 here, a terminal 1 here. So we know that that's not going to be the case. And we know that it's excess, so we know it's not going to be a double bond here.
What's the definition for terminal?
At
For-
the end carbon.
Oh,
Right?
okay.
So in that case, you have a bromine at the end of the molecule. So that would be terminal.
Gotcha.
Okay. Does that make sense? So it's not gonna attach that. It's gonna have, because these guys have exposure, this guy is gonna react first before that. And if we have excess, and something else, we could affect this. But those ring structures, that that benzene ring is so stable, it takes a lot to get there. So we'd have to add heat or something to sit there and help disrupt that ring. Okay, where that triple bond there isn't as stable. So it's like, okay, yep, sure. You know. Let's go. Okay. Let's see. Okay, so let's go ahead and take it. Can we take a 5-minute break? Do you guys mind if we take a 5-minute break? Okay. Stretch your legs.
Sure.
Go to the bathroom. You know, do what you need to do. Okay. Go grab some information before they close. Okay, so the next type of reaction that we're going to be talking about is the acid catalyst. So the last reaction, that was halogenation. Okay, just for the record, halogenation was the last type of reactions that we're talking about. The addition of halogens. Okay. Okay, now acid catalyst, catalyzed addition of water. So basically we're going to be adding water, right? So when we were working with the double bonds, we added water with sulfuric acid, right? Then we end up with an alcohol, okay? And it's a secondary alcohol, not a primary alcohol, right? Remember? Okay, so in this case, we're not going to end up with the alcohol, right? We're going to end up with a ketone, okay? And the reason why we're going to end up with a ketone, well, technically, we're going to end up with a enol, but that enol is not going to be stable, and we're going to end up with a ketone. So at the end of the day, we're going to end up with primarily a ketone. This guy's going to act as an intermediate. Okay, enol, you guys want to know what an enol is, right? Okay. Okay. So these guys here, now they're a form of isomers, right? But these guys are called tautomers. Okay. The process of going from the enol to the ketone is called tautomerization. Okay, so if we have a triple bond, the first thing that's going to happen is that triple bond added with water and sulfuric acid, it's going to form the alcohol. Now that alcohol is then going to tautomerize to form a ketone. Okay. So this process is going to be called, going from tautomerization, is going to be called ketone enol interconversion. Okay. So next slide. Okay. Okay, piece of cake. Yes, the enol is less stable than the ketone. So the double bond. It's because of the double bond. Yeah, double bond, and you basically have a double bond in this alcohol acting on that carbon. That's going to be less stable than having a double bond attach it to the oxygen. Yeah. Okay, mechanism. Okay, so we have, in the case of the alcohol, the secondary alcohol, the electrons from the oxygen is going to act on this bond, then the double bond here is going to act on that water that's going to be available, right? Or that the hydronium ion that's going to be available. And then that's going to act on the electrons on the water. And so then you're going to end up taking the hydrogen here, okay, and then the water molecule is then going to act on the enol, the hydrogen on the enol. That's going to interact on this hydrogen, and it's going to allow the formation of that double bond. So this is going to result in a double bond formation. So we're going to end up with a double bond. We have this, and then we're going to have a plus here. So then this is going to allow for the removal of the hydrogen, and so you're going to end up with the hydronium ion as a result of that. You're going to end up with your ketone. So this results into the double bond. This ends up resulting in a single bond. Right? Trade-off. Okay, so if we have a symmetric, then it can end up, we're going to end up with one product, right? If we have unsymmetric, we're going to end up with two products. Okay, so very similar to what we saw with the bromines. I mean, when we added the excess bromine and stuff like that, the dihalides, or in the case of the geminal. Okay. Questions? Concerns? And you guys can find this on one of your slides. I mean, one of your flashcards, not your slides. Okay. So terminal alkenes are less reactive than internal alkenes. So in the case of us having this terminal alkene here, we're actually using water, and we're using sulfuric acid, and we're using mercury sulfate. Okay, so we have to use mercury sulfate to increase reactivity. Otherwise, it would take forever for this reaction to occur. It wouldn't happen, so, right? So without the mercury sulfate, so we really need that mercury ion to get this to happen. Now, in this case, in the case of the terminal, again, the OH is going to end up here. So you're going to have your enol. You end up with the double bond here, right? So we're going to get the ketone, the enol ketone conversion, or interconversion, resulting in our ketone product. Okay. Now, again, this won't happen effectively. It won't happen essentially if we don't include that mercury ion. So that mercury sulfate adds the mercury ion that acts as a catalyst. It helps that process. Okay. I believe it's called mercurial mercurial ketonation or something along those lines. I have to look to be sure. So when you guys talk about the naming of different ones, So if it's mercurial, then you know that you're including mercury in that reaction. Okay. Questions? Okay, so let's talk about the mechanism. So here, we're going to be using the mercury. The mercury is going to provide the electrons to the carbon. The double bond is going to provide the electrons to the mercury. And so then you're going to end up forming a bond like that, where mercury is going to bond to both carbons. So then water then is going to come along and use its electrons, donate them to the carbon. So then we're going to get the OH here. Then another water molecule is going to come along. It's going to interact with the hydrogen. The hydrogen is going to transfer its electrons to the OH. So then we end up with the hydroxyl group over here. So on the secondary carbon. And so we then, oh, I forgot this part here. The water is also going to transfer its electrons here. And then these guys are going to transfer its electrons to that, breaking that bond, resulting just in that the mercury ion associated with that, with the primary carbon. So here we're going to get our mercuric anol, and this mercuric anol is then going to go to a mercuric ketone, and then the bond between the mercury and the methyl group is going to act as an electrophile, and it's going to transfer its electrons to that carbon, which is going to result in the double bond. The double bond forming, and then resulting in the hydrogen attaching to the water molecule, forming a hydroxyl. God, I can't think right now. Hydronium, can't even think. The hydronium ion, and then the hydronium ion is then going to provide its electrons just to form water, and we're going to end up with mercury 2+ at the end of the day, the same mercury that we started out with. So at the end of the day, the mercury is going to be added to the reaction and removed from the reaction. So it's going to act just as a catalyst, kind of speed up the reaction. Okay. Questions? Just the catalyst. Yeah. So the mercury is acting as a catalyst because you end up with the same product or the same thing that you started out with, right? So in other words, it's just going to help speed up the reaction. It's just acting as a conduit to get the reaction to occur. Otherwise, it would take forever for this reaction to occur. Basically, it would be so slow that you wouldn't see it in our lab. Okay, so hydrogenation and oxidation. Okay, so in the case of hydrogenation, here we have our acetylene group that's going to be reacting with our borate. And I don't remember what THF is. I think it's tetrahydrofluorine. So in this case, the tetrahydrofluorine is going to act to help drive the reaction. So as a result of this, we're going to end up with this hydrogen is going to act as nucleophile. This is going to be electrophile, and you're going to get your borate added onto the alkene. So then we're going to add the hydroxide ion and peroxide and water. And so then we're going to end up with an anol. And we know that that anol is going to end up turning into a ketone. Okay. Yes, but in this case, the nucleophile is going to be the hydrogen there. So it's going to be that hydrogen there. And then the boron is going to act as the electrophile. Okay. So now you have two different ways of synthesizing the same product, right? What was the first way of doing it? What was it? Mercury, if it was a terminal one. So mercury is going to be used for the terminal. Yes, but how do we get the formation of the anol? You guys remember? Yeah, what is the name of the reaction that we use to get, how can we get a ketone? Yes. What was it? Well, that's the process of going from the anol to the ketone. Okay, that's just only part of it. So how do we get to the part where we're going to go from the anol to the ketone? No. Acid catalyst. Addition of water. Okay. So, or we can say hydrolysis, right? Okay. Acid catalyst hydrolysis. So you're using water to basically, in this case, it's not really breaking down. Well, we're breaking down water. Okay. Questions? Or hydration. Yes, that was only for terminal, right? Because it's going to speed up that terminal. It actually will speed up the other one, but the other one it's going to happen fast anyway. So it doesn't need it, you know. That's right. It doesn't need it. It's going to happen just as fast. Yeah, but that terminal reaction, it doesn't like to happen. So it needs something to kind of get it started. Okay. Okay, are you guys with me? Okay, so we're using boron as an electrophile. So this is just basically showing you that process of using a boron type molecule. Okay. Now you can see that boron is kind of nicely stable, beautifully worked out. You have those 3 bonds that it's attached to. So you can also use 9-BBN, which is 9 boron bicyclo 3.31 nonene. Okay, so in other words, your boron is attached to a cyclic moiety, right? And so, or you could use it, boron that has 2 hydrocarbons that are attached at other ends too. So 9-BBN can be used with all alkenes, and it should be used with terminal alkenes because it'll work well with terminal alkenes. Okay. Questions? Okay. So here, this is a terminal alkene, right? So we can use the boronation oxidation procedure to sit there and get an aldehyde, right? In this circumstance. And then we can use the mercurial oxidation to get our ketone. Okay, so if we have a terminal alkene, we're going to form an aldehyde with this process using the hydroboration oxidation compared to that ketone. Okay, now if we have an internal alkene, we form a ketone. Okay, so this process, if it's internal, this guy is an internal, right? So we end up with a ketone. This guy is terminal, so we end up with an aldehyde. Okay, aldehyde, you guys look, aldehyde ends with the H, where a ketone has another hydrocarbon attached to it. Okay. Okay. Which product would be isolated from the reaction shown? Sampula, are you there? Oops.
Yes, we're here.
Okay, good. Got some answers? A. We have one for A. You said M, or did you say damn? Okay. Okay, there's six. I mean, there's 8 of us. I have one answer so far. D as in donkey. B as in boy. E as in elephant. You guys are just gonna, we're just gonna put an answer on everything, huh? I may not get
I'll
it
go
right, but
go A.
you're gonna go with A, you said?
Yeah.
I'm going to go with E.
E or B?
E as elephant.
Elephant. Okay. Sampula? Well, Sampula says E. What was it? Go with A. The correct answer is E. This guy is what? It was at 9 bromo bicyclo. Okay, so we know that if this guy is this a internal or is it a terminal alkyne? It's a terminal alkyne. So we know that it's a terminal alkyne. Terminal alkynes are going to give us aldehydes. That's right. And this is an aldehyde, right? This guy, this is an anol. This guy is an anol. This guy is a crazy anol. And then this guy is a ketone, right? So we know that we can get rid of all of these because we know that these guys are going to be transferred into either this or this, right? They're going to be tautomerized. Tautomerized. Yeah. Yeah, if there was a carbon here, let's say we had a carbon here, just a CH here, then that would give us a ketone, right? Because it's eternal, it's a terminal, then we're going to get that aldehyde. Okay. Cool. Okay. Did you need to see? The answer was E as an elephant. Okay. What time does this class end? 5:45. Don't push your luck. I'll keep you here another hour. Huh? Watch me. Yeah, they'll just get their OChem section real fast. Okay, so here this is basically the addition of hydrogen to form an alkane. So here we're going to be adding hydrogen gas. We're going to be using the platinum metal as a catalyst. Okay. So the first thing that's going to happen is that the hydrogen is going to, we're going to use the double bond. I'm sorry, the triple bond, thank you. Triple bond to donate its electrons to the hydrogen. The hydrogens are then going to be added to both carbons. Then it's going to happen again. Okay. So again, this is one of those experiments that we have to have excess. If we have equivalent, then we get just the alkene. If we have excess, we'll get the alkane. Okay. So it's kind of like what we saw with the bromide gas or the chlorine gas, okay, earlier. So the halogenation So in this guy's called hydrogenation, would be the name of the reaction. Okay. So if we wanted to just stop at the alkene, we're going to use the Linder catalyst, right? Or equivalent, right? Okay, so what the catalyst does, what the metal did as well, was to deliver the hydrogen to one side of the triple bond. So it's going to deliver the hydrogens to one side of the triple bond in this case. So then we're going to end up with a cis 2 pentene in this situation. If we wanted to go trans or anti, then we're going to have to use a different way. So the Linder catalyst will result in a cis addition of the hydrogens, or syn. If we use sodium or lithium metals and ammonia, or liquid ammonia, then we're going to end up with trans. Okay, so sodium or lithium with ammonia, trans, Linder, cis. Okay. Questions? Okay. So the mechanism for trans. Let's see. So, triple bond donating its electrons to each of the carbons. Then we have the sodium metal donating its electron to that carbon. So then we result in a radical forming. You guys know a radical is just the formation of, that one lone electron that is unstable, right? Okay. So then the sodium has a plus charge. This guy gets that minus charge because it has that one extra electron. Then these electrons are then going to act on the ammonia. Then the ammonia, on the hydrogen on the ammonia, then the hydrogen is going to donate its electrons to the nitrogen, and then that's going to form the ammonium ion. And then you're going to get a vinylic radical. So then you're going to have another sodium that's going to come along. It's going to donate its electron. And then you're going to get the sodium ion. And then you're going to get vinylic anion. And then the electrons from the vinylic anion it's gonna donate its electrons to the hydrogen. The hydrogen's then gonna donate to the ammonium, and then you're gonna be ammonium ion, and then you're gonna end up with a trans alkene. Okay, questions? Concerns? Cash? Okay, good. Here's a question for you. Which reagent is the best choice for completing, which reagent is the best choice to complete the following transformation? No yawning. So how many people say A? Cameron? Sampula says A. Kayla, what do you say? Sampula, you got a question?
No, just raising my hand for A.
Okay,
A.
said A. Okay. A. Abby,
Yes.
A, B, C, D, E, or F?
I was in between A and B, but I'm gonna go with A.
Okay. The correct answer is A. So if it was cis, it was like this, what would it have been? Did you say E as in Edward?
Yeah, A.
Okay. Why trans? Has to do with that radical. Okay, so that trans radical is going to be more stable. The cis radical is going to be less stable. So it's going to have preference for that more stable trans radical. Okay. So if the radicals both sided, then it's going to cause problems, right? Trans radical, radical on one side, and then you have the double radical on the other side, then more stable, opposite from each other, compared to when they're on the same side, they're going to bobble each other. So this electron repulsion or steric hindrance, right? You guys remember steric hindrance? Getting in the way of each other. Steric, kind of getting in the way of each other. So remember when we were turning the models, and then if we turn the models, they're both on the same side, they start, the molecule's so big on one side, it'll start bumping to each other. Steric hindrance. Okay. Okay. Which of the following statements is not true? A, alkenes undergo electrophilic addition reactions. B, alkenes are less reactive than alkanes in an electrophilic addition reaction. Sodium in liquid nitrogen is used to form cis alkenes. D, catalytic hydrogenation of alkenes in the presence of palladium and carbon gives complete reduction. E, the reaction of alkenes in water under acidic conditions give an enol. See, Okay, everybody says C. I should say the not true answer is C. You're a little early, I think. You can just hang out in the back. It's fine. Okay. Let's see. Okay, so we'll pick up here on next Monday. So we finish this chapter. We only have a few more slides. Just started. We have 6 minutes left. You want your 6 minutes? I'll give you your 6 minutes. Okay. What did you say? Okay, so the relative electronegativity, this just basically shows you that in terms of relative electronegativity, the sp is going to be more electronegative than the sp3. Okay, so that means that your triple bond moieties are going to be more electronegative than your single bond. Okay, so what does that mean in terms of polarity? Who's going to be more polar? The triple bond, right? Which we saw earlier when we were looking at the boiling points, right? Okay, so this is just kind of confirming that. So when we look at in terms of most acidic, also because of that electronegativity, those guys are also going to be more acidic. So triple bonds are going to be more acidic than single bonds. Okay. Good. Yep. It's going to be, so your pH, it's going to be directly proportional, right? Because it's your pKa. So if you guys remember, back in the old days, so how do we calculate how would we calculate the pKa? So first off, let's start off with the equilibrium constant, right? So this will be the equilibrium constant for an acid, right? Which is going to be equal to what? What does the chemical equation for an acid look like? You don't remember the chemical equation for acid? The generic chemical equation for?
It's pKa times minus log. I forget.
Yeah, but that's how we would calculate it. Would be the
Oh.
I said the chemical equation.
Oh, the chemical equation?
This represents an acid. When an acid dissociates, it dissociates into what? Does it dissociate into water? The hydronium ion, okay, so that H plus AQ, or we can say H3O, right? And A being a generic. Plus. Come on down. It hasn't been that long. And you guys see this? Yeah, this is a full class. It's HA, okay? H representing hydrogen, A representing what? The conjugate, right? So then what is going to be the other product that I'm going to get? What was that? The base, and what would that be in this case? Would it be H? No. What was it? Hey, look at the reaction. If we're using it as a generic, right? Okay, let's use a real acid. HCl. Alkene. What does that dissociate into? Okay, so then this would be a minus, right? Oh my gosh, it's like everything that you guys learned, you're just throwing it out the window. Okay, so you guys got to remember the things that you've learned this stuff, right? You see this, you've seen it like 50 million times because you tutor for 2A. Come on now. Now you guys are using weak excuses. Okay, so then we know that the acid is going to be dependent on what when we calculate, or the equilibrium constant is going to be dependent on what? Come on now. You guys got this. I know you got this. There we go. Concentration of the products of the reactants. Okay, you guys remember that? Okay, so then if we take the pH of this, right? So the pKa is going to be dependent on directly proportional, right? As this guy goes up, this guy goes up. So if we take the pH, which is log of both sides, log of this, right? It's going to be directly proportional. As this guy goes up, this guy is going to go up. Okay. So if our acid is getting higher, which means that its pH is higher, which means it becomes more basic, right? Then that means that this guy is going to become more basic. If we look at these numbers, the pKa is 25. This guy is more acidic than this guy. Okay, makes sense? Okay, don't forget the things that you've learned. You guys, you put a lot of time into learning that stuff. Don't throw it out the window, okay? I know you know it. Oh, we're all having Mondays today. Today is a Monday, you know? Okay, so I'm gonna let you guys go. Mauricio is gonna have to stay anyway, so he's got to stay for another class.